Alright, hey guys, what's going on? So today we are going to be covering a geometric understanding of the Einstein tensor. We're getting to the point in GR where we're going to explore a lot more advanced, interesting things in GR. We're going to start applying more physics to all these tensors we've been talking about and all these scalars. And then from there we're going to get really, really advanced. We're going to talk about different types of spacetimes, and we're going to talk about the Weyl tensor. We're going to talk about more interesting and more advanced types of tensors as well. So with that being said, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to contribute to the channel, where I will be making more videos and notes on everything that I'm talking to you about. And with that being said, let's get straight into the topic. So today we are going over a geometric understanding of the Einstein tensor. So a lot of videos actually don't talk about the Einstein tensor in the kind of way I'm going to talk to you about today. And after this, we're going to get into some identities that involve the Riemann Curvature Tensor and how that sort of relates to the Einstein Curvature Tensor, because these two things are sort of intrinsically linked with one another via the Riemann, or via the Ricci tensor and via the Ricci scalar. And we're going to see exactly how that plays out. So the picture we want to keep in our mind now is not a sphere tracking volumes, not a sphere tracking the deviation from a surface area. We actually want to take a look at a plane on this manifold. One of the things that we want to also keep in mind is that the manifold that we've been working with is a four-dimensional manifold, right? So this manifold right here is a four-dimensional manifold. It has the temporal dimension, and has the three spatial dimensions. The aim here is to collapse all of that down into a smaller dimensional manifold, okay, or a tangent plane, if you will, to that manifold, okay, and that's what the Einstein tensor is going to really help us do here. So the plane here, this is sort of kind of a weird way to think about this, because the manifold looks like it's two dimensions in this case, or three dimensions, if you will. Because it's got some curvature in one direction, and it's got lines that indicate perhaps a coordinate system on that manifold. However, this is abstract. This manifold fundamentally is an abstract object. It's really hard to actually conceptualize four dimensions, but the manifold itself is four dimensions, and we want to collapse that into two dimensions. Okay, and let's see how we're going to do that. So this is that two-dimensional plane I'm talking about. We're going to consider a point P, and we're going to first start off at this point P by identifying a vector, this vector being S, okay? And what we're going to do in this video is we're going to take that vector S, and we're going to subtract it in this particular way from the metric tensor, okay? And when we do that, once we apply some vector t to this object, then we're going to get something that's going to start looking like a projected version of the Riemann curvature tensor. So let's see how this works. So we're going to consider the following object. This is that object I initially had talked about, which is this right here, okay? And what we want to do here is we're going to apply this to t, just like I talked about. So when we do that, we raise the index on t, or we lower the index on t, right, with a metric, and then we just have t hanging out in the end here. Okay, so this object is orthogonal to S, right? Here's that vector S. This is orthogonal to that vector S. When we say orthogonal, I'm going to mean that the inner product of t, or of this object, with S is 0, okay? So, and let's see why. This is orthogonal to S, because if we apply this object now to S, we get this, okay? So here's that object, it's right here, we're applying it to S, we get this. Now, if we can zoom in a little bit more here, and let's take a look at this now. So this is going to stay the same. This guy here, this S mu and S mu, well, that's we're going to demand that is going to be 1, right? That's really an inner product of a vector with itself, okay? And then we have SV, T, V, or not V, right? Nu, right? So T mu, S mu, S nu, T nu, and then, and so we get this now, right? And these are just dummy indices, right? We sum over all these, we sum over all these. So this is actually just going to be 0 because it's one is the same as the other. So we're subtracting it, we get 0. So that means this object here is indeed orthogonal to this object here. So this is highly suggestive because it's going to say, we're going to say that this object here, it sort of projects t. If we identify some t, some vector t, it's going to take t and make it orthogonal to s, okay? And that's how we're going to define the plane that we're on, okay? Because once you define a vector, two vectors, you can essentially identify a plane associated with those two vectors, okay? Because it takes two vectors to define a plane. All right, so let's erase that. Don't want to erase the title. So like that. So let's get to the second part here. So let's consider now this right here, right? So this is a total contraction of the Riemann curvature tensor, where we have delta beta, here's our delta and beta, and our alpha and gamma, okay? And we'll see exactly why you could have, right, alpha, delta, and beta, gamma. I'm just doing it like this for right now, and we're going to see how this plays out, okay? So this object here, here's that, and we're going to subtract it. We're going to subtract s from it, okay? So these are the components of s, or this is s in component form. I'm going to do the same thing with g delta beta. So here's g delta beta right here, and we're subtracting s from it again. So, and then here's the Riemann curvature tensor, right? So this is still a contraction. This is the same thing as this side here. We're just adding, or we just have this extra subtraction of the s vector. If you recall, the s vector was the vector that was orthogonal to this plane, and what we're going to do is we're going to find the object here, okay, that lies in that plane that's orthogonal to s, okay? And so in this case we're finding a tensor, right? So this is the Riemann curvature tensor that is going to be orthogonal to it, okay, right? So you can sort of think of this as, almost think of it as, okay, you have some Riemann curvature tensor defined for some point on a manifold. So this is a little bit weird to think about, right? So you have some Riemann curvature tensor that's defined in the four-dimensional manifold, but it is orthogonal to another tensor, okay? We're going to figure out what that tensor is. Quick hint, it's going to be the Einstein curvature tensor. But let's see how this plays out, okay? So we first multiply everything out. Okay, so multiply this by this and this, right? So we get this, and then we multiply this by this and this, right? So we get this one with that. And you could sort of see how this all sort of plays out, right? This is really just FOIL, right? And then we can get rid of this guy here because these are all symmetric. This is anti-symmetric about alpha, beta, and gamma, delta. And we haven't really talked about this yet. We're going to talk about this in the next video. For right now, we'll just say it is anti-symmetric, and when you multiply something that's anti-symmetric with something that's symmetric, this is anti-symmetric. you get 0. So we can cross that term off and we end up with a term that looks like this in here, okay? Again, we're going to go over the antisymmetric properties of the Riemann curvature tensor in the next video. But for right now, let's just establish the Einstein tensor and get an understanding of what this is going to look like. Okay, so this is contracting to the Riemann scalar, or the Ricci scalar, or the scalar curvature. And then we get this here, right? Well, this is just two copies of the same thing because we're summing over dummy indices, right? So we have all of this right here, okay? And we can see that we can also raise, right, this is, see, I have 5 things right here. Actually, I'm not raising anything. What I need to do is I need to get rid of this alpha. That should not be there. Right? And then we have R again, so we didn't do anything here. And we are raising now alpha and gamma, right? So with the metric, so we get beta, delta, all right? And then what we are doing now is we go from, so we can sum over this is really just this G beta delta S beta delta. We're not really adding anything to this, right? Because they're going to sum over each other, and then this is essentially going to go to 1 because this is an inner product with S and itself, and then we just have the metric. Okay, so this isn't really doing anything to the equations. Okay, so but what this enables us to do is it enables us to factor out S beta and delta, right? So here's our S beta and delta, and we have R with the metric, and then times 2 times the Ricci tensor. Okay, and then we're going to define this guy here as the Einstein curvature tensor. So this here is the Einstein curvature tensor. We have this, when we say 2, when we put a 2 out here, then G beta delta is going to equal 1/2 RG beta delta minus R beta delta, like this. And this is important. This is going to show up in the Einstein field equations. All right. Let's erase that really quick. So the Einstein tensor is a projection, if you will, of the Riemann curvature tensor on an n-2 dimensional surface, right? Because this surface is 2 dimensions. This is we've defined this to be a 2-dimensional surface, which is n-2 because the manifold itself was a 4-dimensional surface, right? So we've now found a tensor that's analogous to the Riemann curvature tensor. It defines curvature, but in 2 dimensions lower than the actual manifold itself. Okay, and why is this important? This is important because when we start talking about the Einstein field equations, right? The Einstein field equations, we have we're going to have T mu nu. We haven't talked about this object yet. This is the stress energy momentum tensor. The hypothesis that Einstein had was that this is equal to some other tensor that has to do with curvature, G mu nu. This is 2 indices, so the other thing has to be 2 indices. It would be nonsensical to put R alpha beta mu nu on this side because this is a 1-3 rank tensor. This here is a 0-2 rank tensor, right? This is a 0-2. Oops. a 0-2 rank tensor. So we need a 0-2 rank tensor on the side, and that's going to be the Einstein Curvature Tensor. So the Einstein Curvature Tensor, or the Einstein Tensor, defines curvature just like the Riemann Curvature Tensor does, but it has two indices instead of one. Okay, you might think, okay, well, why can't we just use the Ricci tensor, right? And the answer to that question is going to be hidden in this idea of preserving volumes and preserving shapes. Okay, what we found out with the Ricci tensor is that the Ricci tensor tells us something about volumes, doesn't necessarily tell us something about the curvature of space. Okay, and what that discussion is going to lead us into the Weyl tensor, right? Because the Weyl tensor is going to sort of complete the picture with the Riemann or with the Ricci tensor and tell us, okay, volumes are going to be distorted, and that's what the Ricci tensor is going to tell us. Shapes are going to be distorted, and that's what the Weyl tensor is going to tell us. Okay, but for right now, we're talking just about the Einstein tensor. The Einstein tensor tells us something about the curvature. Okay. And we're going to get into talking about the trace of these tensors, how the trace plays a role in these objects as well. Because remember, we can think of these as matrices. We can think of these guys as matrices. And when we think about them as matrices, we can start conceiving of things like the trace, the determinant of all these different types of things, okay? And so, with that being said, let's do a grand summary of what we've talked about so far. So, what we have is, we talked about the connection, right? So the connection, this is a while back. The connection, we took the metric, right? If you recall, the metric was, if we're on some curved manifold and we're standing on the manifold somewhere, we're holding a ruler and we're holding a clock, right? That doesn't look like a clock. The metric is going to tell us everything about measuring times and distances in this space-time manifold. Okay. Derivatives of that metric, right? So the metric, what we measure here is our metric, mu nu. Okay. So derivatives of the metric make up the connection, right? And the connection tells us something about how we can compare vector spaces at each point in the manifold. Right, so derivatives of the metric get fed into the connection. Derivatives of the connection get fed into the Riemann Curvature Tensor. And then the Riemann contraction of the Riemann Curvature Tensor gives us the Ricci Tensor. And I'll just write all these down. So the connection, Riemann, Ricci Tensor, Ricci scalar, and then the Einstein tensor. These are the big boys these are sort of the big boys in GR, right? So there's going to be other things that we're going to want to talk about, other different types of tensors that are going to tell us something about the curvature and forces that play a role in distorting objects in space, and that's going to get us into topics on the Weyl tensor, and the potential that goes into generating the Weyl tensor, which is the Lanczos tensor. Briefly speaking here, the Weyl tensor, we're going to call it C alpha beta mu nu. The Weyl tensor is part of the Riemann Curvature Tensor, and it's specifically the traceless part of the Riemann Curvature Tensor. And what we're going to be able to find is that these tensors, the Lanczos tensors, these are going to be three components, say alpha, beta, nu, that generate these guys, okay? And they're sort of analogous to when we talk about in electromagnetism, F mu nu and A mu. There's an interesting an interesting link or an interesting analogy between these two guys, and we're going to talk about that as well. Okay. And so we have the Weyl tensor, Lenskos tensor, and there's Blavatsky tensor also. Tensor. A lot of these are very esoteric tensors, and we're not going to get too much into these. These are probably going to be something I'm going to put more in my tensor calculus playlist. But nonetheless, these tensors are super important. We're also going to dive into more of the physics as well, right? Because this is a physics channel. This is a physics playlist, and we're going to be talking about the Schwarzschild metric, the Kerr metric, the Reissner-Nordstrom metric, all these different types of metrics that sort of tell us things about black holes. Okay, so with that being said, I hope you like this kind of content. Make sure to hit that like and subscribe button, and make sure to go into my Patreon page if you want to support the channel, and if you're interested in getting the notes for these as well as they slowly come out. So I will see you guys in the next video. Bye.